It is often handy to find the center of gravity of some structure or other, and center of gravity is just the place where the thing is balanced. So you see that in sculptures or mobiles like this one here. I think this is in the National Gallery. So each one of those arms has a center of gravity, and if you attach a wire right there, that arm will balance. Center of gravity is useful in things like loading cargo into a trailer. So if you know where the center of gravity of the trailer is, you would do well to put the center of gravity of the cargo there too, wouldn't you? Each object has its own center of gravity, and you can put those onto a bigger object. So like here are some conveyors and motors and things on a big old beam, and each one of those has a center of gravity, which I've marked with a target-shaped thing here. And for each one of those things, like this one conveyor, you can figure out where its center of gravity is located. That's where this one's is. And then, instead of looking at this big old complicated glop of stuff, you can simplify it and draw one arrow for each center of gravity of each component. So here's that conveyor we looked at. There's its center of gravity. There's the motor. There's its center of gravity. So now you have just a simple free body diagram of a beam with a few arrows on it. And now it's much easier to figure out what is the load on the axle, or what is the bending moment in the middle, and that sort of stuff. Let's back up and think about this a little bit more. So let's say you have a shelf with 2 books on it. Each book weighs 10 pounds, and they're the same distance from each end of the shelf. So what's the total weight on that shelf? And where is the center of gravity of that assemblage of books and shelves? Well, the total weight must be 20 pounds, and if you put one 20-pound book on the shelf, it would have the same net result as those 2 10-pound books, wouldn't it? That 20-pound book is the resultant, and you might remember from structures discussions, the resultant is the one force that has the same net result as the individual forces. And the handy thing is that the resultant lands at the center of gravity of the thing. So here's another example, just different numbers. 2 6-pound books, and they're each the same distance from the end of the shelf. There's the resultant at the bottom of this slide, the one force that has the same net result as those 2 books. How big is that resultant? And where is that resultant? Well, that resultant has the same weight as those 2 individual weights. And because these things are located symmetrically, that resultant must be centered, right? So if it's a 12-foot long shelf, the resultant is 6 feet from one end. So there's the resultant and the location. So there's the center of gravity of that bookshelf with books on it. What do you do if the things are sitting on the shelf and they're not symmetrical? They're different weights and different distances. And we're trying to find the resultant and where it's sitting, because that is where the center of gravity is. First of all, how heavy is that resultant? Well, the weight of the resultant is the same as the weight of the 2 books. So that resultant must weigh 10 pounds. Where is that resultant? Turns out that the moment caused by the 2 books is the same as the moment caused by the resultant. And remembering back from structures class, remember that moment is force times distance. So force times distance stuff for the small books is the same as force times distance stuff for the resultant. So the moment caused by the 2 books, let's do this. 4 pounds times 2 feet. 6 pounds times 6 feet. That's how far it is all the way to the end. So the moment caused by those 2 books, boiling the numbers down, getting out our calculator, the moment caused by the 2 books is a negative 44 foot-pounds. And why is it negative? Because they're clockwise. All right. And the moment caused by the resultant, we don't know what its distance is, but we know that it weighs 10 pounds. So its moment has to be, and it's also clockwise, so its moment has to be 10 pounds times x feet, and negative. So the moment caused by the 2 books equals the moment caused by the resultant. Let's just write that down in some math stuff. Negative 44 foot-pounds equals negative 10x foot-pounds. So 44 equals 10x. Ha-ha! Turns out that x, the distance to the center of gravity, is 4.4 feet. 44 divided by 10 is 4.4. So there's the center of gravity of that thing. Let's do another one that looks a little bit more like a beam. Here is a beam that weighs 5,000 pounds, and sitting on it is a box that weighs 8,000 pounds. Well, this is a uniform beam. It's all the same material. So that 5,000 pound weight, we could say, is centered on the beam. The box, as you can see, is not centered on the beam. Question is, where is the center of gravity? And before we start figuring, let's think to ourselves, where would we predict it might land? Would the center of gravity land smack in the center? No, probably not, because there's an 8,000 pound weight over here. Which side of the center is it likely to land? I'm going to say it's probably going to be to the right of the center, because that's where more of the weight is sitting. Let's see if I guessed right. So let's work through this. Here's a free body diagram. Replacing our picture, there's an arrow for the 8,000 pound weight, and it was 20 feet from point A, so there's my 20 feet. Here's an arrow representing the 5,000 pound beam, and notice I've drawn it right in the middle of the beam. If it's a 30-foot beam, that's 15 feet over. Alrighty, so there's our free body diagram. Now let's figure out the resultant. How heavy is that resultant? Well, the weight of the resultant must be the weight of those 2 forces. Those 2 forces, 5,000 plus 8,000 equals 13,000. So, ta-da! The resultant must weigh 13,000 pounds. So that's the single force that would have the same net result as those 2 individual forces. Okay, now the moment caused by the 2 loads is the same as the moment caused by the resultant. So let's work through that using our moment equals force times distance. Okay, so the moment caused by the 2 loads, force times distance, there's the 5,000 pound load times 15, negative because it's clockwise. There's the 8,000 pound load times the 20-foot distance, negative because it's clockwise. So getting out our calculator and crunching these numbers, negative 75,000, negative 160,000 equals the total moment caused by those 2 forces is negative 235,000 foot-pounds. All right. the moment caused by the individual loads is the same as the moment caused by the resultant. So the resultant must have a moment of negative 235,000 foot-pounds, something. What is its distance? So the resultant weighs 13,000 pounds and its distance is x. Its moment is negative 13,000 x. The two loads we just figured out have a moment of negative 235,000 foot-pounds. Their moment is the same as the resultant's moment, so the moment of the two loads, negative 235,000, equals the moment of the resultant, negative 13,000x. And by the way, I should have mentioned this earlier, if you have a negative something equals a negative something, you can get rid of those negative signs, can't you? You could just multiply both sides times -1 and make the minus signs go away, like that. So that's cleaner, a lot of people think. Okay, we're trying to find out how far is x. If 235,000 equals 13,000x, we could divide both sides by 13,000, and the 13,000s cancel out, and we are left with 235,000 divided by 13,000 equals 18.077 equals x. That's how many feet x is. So where is the center of gravity? It's 18.077 feet from A. That's the location of that 13,000 pound resultant that has the same net result as those two individual loads. And that is the location of the center of gravity of this beam with the loads on it. So here are the individual weights. Here's the resultant sitting at the center of gravity. And at the beginning, we were guessing that probably the center of gravity was going to be a little bit to the right of center, because that's where more of the weight was sitting. And it turns out, yes, we guessed right. It's a little over 18 feet from A, so it's a little over 3 feet past the center. So that's where the center of gravity is sitting.